Mr. McBrien. This is SCH4U, Bonding Theories. What we'd like to do today is talk about several theories of how bonds form in compounds. Now, so far, we've mostly talked about elements when you think about it, mostly talked about individual atoms. But we know very well that atoms arrange themselves to form compounds. And we're in a position now to move through several theories of why this occurs. One of the most fundamental things in nature, why it occurs, and in fact visualize some of the ways that we have looked at these theories. So it's a good idea for us to start around the Lewis theory of bonding from back, almost exactly 100 years ago. And the key points around Lewis theory is that the noble gas electron configurations are the ones that are most stable. And these stable octets can be formed through the transfer of electrons from metals to nonmetals, as is shown in this reaction between sodium metal and chlorine. But stable octets can also form through the sharing of electrons between nonmetals, or covalent bonding. And it's these covalent bonds that we're going to look at in detail today. But one of the fundamental ideas that we have to keep in mind is that electrons are most stable when they are paired. So now we can introduce some new tools that will help us to visualize some of this pairing and visualize molecules in general. So here we see electron dot diagrams. Each of the red dots in this picture represents an electron. We can see a reaction, a hypothetical reaction between hydrogen atoms and an oxygen atom. 6 valence electrons arranged around oxygen, 1 each for the hydrogens. And when they react together, they form covalent bonds, shared electrons between the hydrogen and the oxygen. And you can see those pairs there that are shared. We can simplify this to try to make this diagram a little less busy by replacing that bonding pair of electrons with a simple dash that represents that bond and highlights that there are shared pairs of electrons between the hydrogens and oxygen as well. In this dihydrogen monoxide molecule, there are 2 unshared pairs of electrons. And here's another example here, the reaction between nitrogen and 3 hydrogen atoms to form ammonia. Again, shared electrons, and we can represent these easily as bonds. So this is an excellent way to visualize not just the molecule, but where these electrons are, with which atoms these electrons are associated. Here's another good one. So we can react carbon with 4 hydrogen atoms to form methane. And in this case, methane has no unshared electrons. So carbon has that stable octet associated with it because of the bonds with hydrogen, but each pair of electrons is shared with a hydrogen atom. These electron dot diagrams also help us to visualize a very important type of compound, type of species, called a free radical. Free radicals are atoms or molecules with unpaired electrons. So we have a single dot which represents that unpaired electron. This is a hydroxyl radical here. And another representation of it here as a Lewis diagram. Now, these are extremely reactive substances because these unpaired electrons really want to find a friend. it's important that you understand the difference between this hydroxyl radical here, which is neutral and extremely reactive, versus a stable hydroxide ion that we've seen many times before associated with bases. This, it has a negative charge and does not have any unpaired electrons. You can see that there's a pair associated with the bond between the oxygen and the hydrogen, 3 paired electrons, so 3 electron pairs as well. We would generally represent that in this manner. There's another important kind of Lewis structure we have to acknowledge at this stage. We're going to dig a lot deeper into what we call resonance structures when we get into organic chemistry. But for now, we can accept that when 2 Lewis structures are possible for a given formula, we can assume a hybrid or resonance structure. And when we do this, the electrons are assumed to be what we call delocalized. They're associated with both Lewis structures at the same time. So let's take a nitrite ion as an illustration. The formula for nitrite is NO2 negative, and we could draw the Lewis structure for this into one of 2 ways. On the left-hand side, we have 2 bonds between nitrogen and one of the oxygens, and on the left-hand side, we have 1 bond between the nitrogen and the oxygen, and then the lone pair electrons. And this thing has a negative charge associated with it. But notice that that's entirely equivalent with the other oxygen having the double bond. When we have this kind of situation, usually both of these oxygens are equivalent on any measurable scale. And so we represent that with this sort of double arrow that says it's actually, in fact, not this one, but a hybrid of the 2. And so the other way we can represent this nitrite ion is with what amounts to a half bond between the oxygens and the nitrogen. And this is closer to the truth, as we'll get into in a lot more detail in organic. So this is a key skill for us to understand. Electron dot diagrams and Lewis structures. We need to be able to draw these for simple and complicated compounds. It's a key skill for the rest of this course. So I'd like you to do a lot of practice around this. So here are a series of problems. If we were in the classroom, we'd be writing these on the board, but I invite you to grab a piece of paper and do your best to draw these Lewis structures. The way you're going to achieve this, remember first you want to find how many outer shell electrons are associated with each atom. Draw each atom with those outer shell electrons as dots, and then form the appropriate bonds as we showed in our 3 examples earlier. And some of them are easy, some of them are a little more challenging. I invite you to go and play with all of these as you work. An important one to highlight though, we can have ions like we had with our nitrite ion. So we have NH4 plus here. Just remember that one of the electrons has to be gone. Usually you can pull this from the central atom. So go ahead and work on that and come back to the movie when you're done. Okay, welcome back. So Lewis structures were a tremendous advance in terms of rationalizing the way compounds are put together. However, by the time chemists had started to use these in anger, we were already starting to get an understanding that this idea was a little bit out of date. Valence Bond theory was developed about 15 years after Lewis was working on electron dot diagrams and such. And it's, rather than looking at simple electrons and stable octets, it's actually a quantum mechanical model of bonding that incorporates Schrodinger's equations. The idea is that covalent bonds will form when a pair of half-filled orbitals overlap, and they form a kind of a combined orbital consistent with Schrodinger's equations. Now, these bonding orbitals will contain two electrons with opposite spin, of course. So we get into this kind of model now where we take a 1s orbital, another 1s orbital for two hydrogen atoms, and we overlap these spheres, and we wind up with like a linear addition of these two orbitals to form a combined covalent bond. So it's a change in the actual shape of the orbitals themselves that forms this bond. And consistent with previous theories, the electron density is highest between the two nuclei because of this overlap between the two spherical shells. When we have direct overlap of orbitals, we call this a sigma bond. And this won't necessarily be just between a 1s and a 1s orbital, as we'll see in a bit. So overlapping orbitals can also form between s and p orbitals. So if we take hydrogen and react it with fluorine, fluorine's unpaired electron is up in the 2p orbital. Hydrogen, the 1s, as we covered. If we want to form a bond between these, we need to overlap the 1s and the 2p orbitals. Well, similar to previously, we have a linear combination of these orbitals that form this new kind of probability map. So our covalent bond between hydrogen and fluorine is an overlap of a 1s and a 2p orbital. This is still a sigma bond. And, like with the hydrogen case, it's a lower energy state for the two atoms. So the two atoms, when they don't form a bond and have unpaired electrons, are in a higher energy situation. When they combine together to share those electrons and pair them together, it's a lower energy situation. And that's where the bond comes from. Now, sometimes you'll see this kind of visualization of what we call molecular orbitals. And we'll talk about this in a little bit. You'll cover this more in undergraduate chemistry as time goes on. Essentially, this diagram is an energy diagram consistent with the energy diagrams we've been drawing for orbitals for some time. And we have the energy associated with, now in this case, this is back to our two hydrogen atoms. We have our energy associated with two hydrogen atoms that have no bonding. And we can contrast that with the situation where when we overlap these 1s orbitals, we form this new molecular orbital, and both electrons occupy this molecular orbital. We're not going to go into too much detail about the other situation, but if we have more electrons and we don't have enough space for them in our sigma bond, they can actually pair up as well in what we call an antibonding molecular orbital, where these 1s orbitals are out of phase. And this is actually a higher energy situation, and if we had extra electrons kicking around, they would tend to push this molecule apart. And this is a visualization of why neon atoms will not bond together. Because yes, two of the electrons could go into this low energy situation, but the other two electrons would go into what we call an antibonding molecular orbital and have an equal force pushing the molecule apart. You won't be responsible for this, but it's good for us to have a first look at this idea right now. Okay, so to continue with molecular orbital theory, we have one very important concept that we need to cover here, and that's to do with our friend carbon. This is one of the triumphs of valence bond and molecular orbital theory over simple Lewis structures. If we look at a Lewis structure, the Lewis structure will consider all four electrons So now when it comes to molecular orbital theory, we have one more important thing we need to cover. And that's to do with our friend carbon. Here is the outer shell electron configuration for carbon that we've done previously, with 2 electrons in the 2s orbital and 2 unpaired electrons up in the 2p orbital. Now, Lewis structures consider all 4 electrons around carbon to be identical. That was our methane that we looked at earlier in this presentation. Well, that's a real problem, because our wave mechanical model has our electron configuration here and here in picture and in shorthand form, and it says that 2 of these electrons are very different than 2 of the other electrons. Remember that the shape of those orbitals are different. Everything is different about these. According to the wave mechanical model, carbon should not be able to form 4 identical bonds. Now there's a problem here, and the problem is that extensive evidence has proven that in methane all 4 bonds between carbon and hydrogen are identical. So we've got a big problem associated with a simple molecular orbital theory and carbon, and by the way, many other bonding types as well. So what's going on? How can carbon contain 4 identical covalent bonds? Well, molecular orbital theory was updated then to cope with this idea. And so in addition to the standard theory where we talk about molecular orbitals as combinations of Schrödinger's equations containing multiple nuclei, molecular orbital theory was updated to consider this idea of electron promotion and orbital hybridization. Well, what does all this mean? These are a lot of big words. Well, it's not as complicated as it might seem. What happens in carbon bonding is that one of the 2s electrons is promoted into the empty p orbitals. Now, this doesn't solve our problem completely. That would give us 2s1, 2p3 atomic orbitals, and we'd still have the problem of the 2s isn't equivalent. Well, what ends up happening, in fact, is that the equations for the shape of these get combined together to form a sort of a weighted average of what we've got there. And so in addition to pushing that extra s electron into a p orbital, the other s orbital takes on some p character. And once we've done this, all 4 of the orbitals become identical, and each of these new sp3 hybrid orbitals can form a sigma bond with another half-filled orbital. So we can visualize it kind of like this, where one of these electrons gets pushed over to here, and then their energy is made consistent. And we got another better graphic of that in a little bit. So we wind up with, instead of 1s and 3p, we have 4sp3. So as soon as we have these equivalent orbitals, the repulsion of like charges suggests that these orbitals are going to move as far apart as possible, and they form what we call a tetrahedral shape. So if we take something like methane, then the hydrogens will get as far apart as they can, which turns out to be at the points of a tetrahedron. And if we measure the angle then between hydrogen and carbon, this will turn out to be 109.5 degrees, almost exactly. And so this is an equal angle between each one of these, which means that each one of these hydrogens is absolutely identical to the others. And this is a critical concept in organic chemistry we'll be returning to many times. So now sp3 are not the only hybrid orbitals. We can combine a single s and a single p to form an sp hybrid, which will give us a linear molecule. We can combine an s with 2p to get sp2 hybrids, which then the way to maximize the distance between these is in a trigonal planar arrangement. We have our sp3. Here's another representation of it. The s plus the 3p orbitals combine to form this kind of shape. And we can even go further. We can combine an s with 3p and a d orbital to get sp3d hybridization. And so for molecules like phosphorus pentachloride, we get a trigonal bipyramidal shape, really quite lovely. So we get, in this case, a trigonal planar shape with chlorines above and below the plane. And we can even go further to an octahedral shape where we have an s, 3p, and 2d orbitals to give us sp3d2 hybridization, and we get this kind of shape. So we call this an octahedral shape. Now, one thing that we're not going to get into in too much detail right now, but you do need to keep in mind, is that there are times when unpaired electrons will occupy one of these locations, but we'll cover this in a later point. Okay, so what I'd invite you to do now is pause the movie and have a look at the outer shell electrons associated with these elements and try to explain the weird valences that you see when you work with these. So this should be a fun exercise for you to play with. You can go ahead and look online if you want to after you're finished. Don't forget, whenever you have ions, if it's a negative ion, you're going to need extra electrons. If it's a positive ion, you're going to need fewer electrons. Okay, to summarize, electrons and atoms have predictable configurations. We've covered this previously, but now we have some additional tools to help us out. When we form bonds, the probability function associated with Schrodinger's equations are modified to incorporate what we can think of as a linear average of the individual orbitals. We can have situations where sharing of electrons can occur between different orbitals, and we get hybridization. The hybridization will predict the shape of the orbitals and will share aspects of those original orbital shapes. If you'd like to see some more material on this, there are some extra readings in our class folder, and there's also some additional videos which I would recommend. You can access these from these hyperlinks within the PowerPoint presentation. For your homework, please go ahead and go through the bonding theory worksheet and check out the review note. And again, I'd encourage you to spend some extra time on this sp3 hybridization. It is one of the key concepts of this course and extremely important to your understanding of the chemistry of life itself. Thanks very much, and have a great night.